Right. I have a new mic, which I don't quite know how to use. Welcome back to the third talk of this morning's session. And it's a pleasure to introduce Pierre Vanhove from my PhD, and he will talk about analytic structure of cosmological correlator.
Yes. So thank you very much for giving me the opportunity to present that work here. So the title doesn't look very, I don't know, number theoretical, but after, a few slides of physics motivation, you will see why, it fits, in the topic of the workshop. So actually, this is some work that I've been doing with Thiel, Ivo, and Genia on actually trying to understand the structure of quantum field theory in curved space. So, the motivation is, well, from physics is that essentially, de Sitter spacetime is one of the most, relevant spacetime that we need for the cosmological evolution of our universe, and in particular, for the phase of inflation, where you have this this growth of the scale factor, and then you get an effective metric, for the accelerated expansion that is of this form, which is a de Sitter form. This is the spatial coordinate, this is the time coordinate, and this is the Hubble constant. And the point is that most of the way we think about quantum field theory in terms of computing scattering amplitude, unitarity, analyticity, and all the constraints we have on the data we extract from scattering amplitude, either in string theory or field theory. We can do a lot of things in flat space, but when you go to curved space, it's very, situation is less obvious. And in particular, for the case of de Sitter space, where you don't, you have already the difficulty of defining what is your asymptotic state at minus and plus infinity because of the geometry of the space. Okay, so on the other side, it's really, so here is a quote by Dirac saying that actually we should indeed, have an understanding of the quantum mechanics in curved space, and to in particular understand what are the, what inflation gives to you. So we, as I said, we have the problem is that what we understand very well is Minkowski spacetime, when we have asymptotically static spacetime. Okay, we can as well understand pretty well ADS. This is a curved space, but you can define, amplitude in ADS and then try to mesh it with what you think is the so-called ADS CFT correspondence and try to extract some physical data. But for the case of the de Sitter spacetime, the absence of a timeline killing vectors makes to the definition of the scattering amplitude very dubious. So on the other side, it happened that if you there's a way to trick the computation to define actually a way to, and I will explain you how to do that, to define correlation function in de Sitter spacetime that are mapped to some Euclidean ADS computation, where in the case of conformally coupled scalar, the Witten diagram, that means the equivalent of the Feynman diagram that you draw in this curved space, can be analytically evaluated. And the pinch is that actually we will show that this is multiple polylogs, elliptic. Well, there is elliptic integrals that will give elliptic polylogs, and from that you can analyze the analytic structure of your scattering amplitude. So that means in some case, using a formalism that I will tell you, you will have a full control of actually the scattering amplitude in your curved spacetime, and you can try then to see what means locality, causality, unitarity there. And of course, because the theta spacetime is quite, I mean, you have to be careful about what you do. One way to validate what we did is actually to extract. We will extract actually correction to the anomalous dimension and to fit to see. I mean, if it fits. I mean, physical quantities that and that looks reasonable. So what we want to do is that we want to look at what you call global observable at future infinity. So here, this is a drawing. So here what you have is that this is a metric. There is the minus sign. This is the plus sign, and d is the special. So little d in my talk will always be the dimension of the boundary. Okay. So in most of what I will show you, little d will be free. This is the inverse radius, and the boundary of the theta d plus 1 spacetime is given by this equation, and it's essentially flat space with infinity. Okay. So now, what are the kind of observable you can consider in that setup? So what is natural to consider is to consider what is called the Bunch-Davies wave function. This is the in-out state. This is the wave function that is defined from the path integral in such a way that you set your boundary conditions at t equals 0, and then you let it evolve in time. Okay. So this is you have this is your Bunch-Davies wave function, and this is and time evolves this way. So from this wave function, you can, by the variational principle, varying with respect to this initial condition, extract correlation functions. Okay. And this is the in-out formalism. This is the standard formalism that you are used to when you compute scattering amplitude in flat space. But that's not the most practical way to do the analysis I'm going to describe. So what we are going to do is that, in fact, we will use, because the Schwinger-Keldysh formalism, which is the in formalism, which essentially is to have some operator, a certain number of operator, like a field here, M, that is sandwiched between two Bunch-Davies wave function, one on the bottom, one on the top, and this is actually computing the correlator along a closed time curve. So this advantage, this guy is defined from phi 0. So the phi 0 you integrate over it, and then you glue the two of them, and then in the middle you have your operators like that. Okay. So, and this is what we are going to compute, and I will show you that you can analytically compute them by some trick. So this is the geometry of your the theta space. Okay. Here is if you change the sign here. Okay, so I've specialized already to the case of d equal 3. Okay, so yeah, d plus 1. Okay. Specialized to d equal 3. Okay, but then if you change the sign, then you go from this one-sheeted geometry to the two-sheeted one, which is actually the Euclidean ADS space of, the boundary is dimension d, like it will be dimension 3, and there is here something that will correspond to the upper half plane, upper Poincare plane, and this is the lower Poincare plane. And here is the time direction. So here for this sheet, x0 is positive. For this sheet, x0 is negative. Right? Okay. And the thing is that we will be mapping the computation to that, and then going back to that at some point. So in a Poincare patch, the de Sitter geometry can be parameterized in this way. So x naught is the time component, and xi runs over 1 to d, and you have x1 goes 1 to d, yes, and xd plus 1 is given by this, okay? And here this is for the Poincaré patch for this one. For this one, this is similar. There are a few signs that are changing, and what you do is that you have here a space that is so the case when the case I will use in the computation is when the boundary space has dimension 3. So this is R3 times Z positive. So this is not the full R4, it's just this half space. And this one, this is the negative part, okay? And the two are related by the analytic continuation, Z to I eta, A to minus I eta, which is responsible for the flip-up sign that you see here. And locally, you have this metric that is almost you are almost a flat metric modulo this conformal factor, and that's going to be important. So now what I want to do is that I want to define what is the correlation function. So as you do in flat space quantum field theory, it's natural to look at path integral that you couple your field to the source. Okay, so you have your source, but here because you are in this Schwinger-Keldysh formalism, then you need to have the source that are time order and anti-time ordered. So there is a time ordering that you have to pay attention to that. And there is the time ordered source that is coupled to the field that is time ordered, and the anti-time ordered source that is coupled to the anti-time order. And here is your action that in a minute I will show you. I will use is the phi to the fourth action. And on that, what you do is that you do a Wick rotation. So you want to map a computation on that space to a computation on that space, okay, through some Wick rotation. So the thing is that when you do this, when you have a field, what's happening is that you have to pay attention that there are two components of the field. There is the field, so the field has dimension delta. So there is here a phase factor that depends on the conformal dimension of the field and the shadow. So there is in this Wick rotation, the field is decomposed into what I call phi plus and phi minus. And the relation between the dimension, the phi plus and phi minus, is delta plus delta minus equal d. Okay, and so for me, delta plus will be 2, when d equal 3, and delta minus will be 1, and this one is the field and this one is the shadow. Okay, so when you say a time-ordered source, do you mean when you expand exponentially? Yes, that's it. Yes. I mean, in the paper, we have been extremely careful about the definition of the Green's function and all of this, but I mean, it's so the thing is that we are using really yes. So in the eta, so it depends if you use the eta and the z, but in the eta variable, so really time ordering or anti-time ordering means really that we are paying attention when you look at the 2-point correlations, that there is the theta function that tells you how you order the field. Okay. So one of the upshot of this analysis is that it was proposed by Di Pietro, Gorbenko, and Komatsu that actually all the correlation function you compute here in the Sitter space can be obtained by a variational principle obtained on an action that is actually just the Wick rotation obtained on dust. And if you look at a scalar potential that is phi to the fourth with a coupling that is lambda, that is minimally coupled and conformal. So that means the dimension here, delta plus and delta minus, are related to the dimension of spacetime, which the boundary dimension, which is d plus 1 and d minus 1 over 2. So delta plus delta minus is d, as you can check. And this field, of course, this is a conformally coupled scalar, so it's massless, right? but the conformally coupled scalar in curve space, when you write the equation of motion, gets a mass, an effective mass from the curvature of spacetime. So the effective mass of this guy is related to the value of delta. Yeah, okay. I will have to tell something about the renormalization because, of course, we have to pay attention to renormalization. But so far, and what happens is that for any conformally coupled scalar actually in d dimension, so I write it for d equal 3, but in every d that is odd, the action takes this form. So the only thing that changes when d is 3, 5, okay, d is an odd number, is just the coefficient that is here. So what you do is that you have one field that looks like a, okay, the normalization is not missing, is not properly normalized. I mean, if you want, you can rescale so that there is the factor of 1/2, but it has a plus sign. So this is a propagating field with effective mass m. This one looks annoying because it looks like a ghost, but it has to be there because it's, if you do a computation in de Sitter, you would just have half of the field and you have plus signs. Yeah, the fact that you have this minus sign is due to this transition between the de Sitter spectrum and Euclidean de Sitter. And this weak rotation, so the potential is 5 to the 4th here. So when you expand this and you use the fact that actually these deltas are given by these values, where d is an integer, an odd integer, then you find that actually in the expansion, I only kept these monomials. So 5 to the 4th, 5 minus to the 4th, and this is this coupling. And in fact, what's going to happen is that there is no yet first principle justification of why this action is the correct one. But if you do the computation of the correlation function by constructing the Green's function, I mean, from first principle, and then organize your computation, and then you compare with what you get from using this effective action, then you find that there's a perfect match. So although there is no a priori, I mean, real justification of why this is working, actually, in practice, I mean, this is the good way to do that. Okay, so now I have this field in curve space, and I need to, as usual, look at what is the Green's function. So you want to know what is the 2-point Green function in your curve space, okay? So here I will have if I want to, I should put a TT, TA, AA, which is for time ordering, I mean, for the precise time ordering. But once I have mapped this thing from de Sitter to anti-de Sitter, I can forget this labeling. But so what I do is that I have to solve this Green's function. So this is the Laplacian in this in a space with this the metric is here. Okay. Then there's the effective mass from the curvature. Then there's 2-point function and the delta function. So it's a well-known result. I mean that actually when you solve this, you get actually something that is an hypergeometric function, right? So the hypergeometric function here, the argument is this inverse geodesic distance in your Euclidean de Sitter space, which when you use the Poincaré patch coordinate, so the bulk coordinate for x is z, the bulk coordinate for y is w, and this is the boundary component. Okay, so it looks like, so there is this quadratic part and this, and you see it's dimensionless. So, and here comes the conformal dimension, and of course, when the curvature goes to 0, I mean, when A goes to 0, you get the flat space limit, and then you see that this expression has the right behavior with the normalization being fixed, I mean, this way. So I want you to look at this and the fact that here there's an I epsilon. There's an I epsilon because when you solve a Green function, you always have to have an I epsilon prescription to define what it means, I mean, as a Green function. So now the thing that happens when little d is 3 and delta is 1, so delta minus is 1 and delta plus is 2. So if I use delta to be 1 or delta to be 2 in this expression, then this guy collapses to this expression. So the hypergeometric function becomes a rational function of k, or k square. I mean, it's a true. And you can rewrite it when you massage it by having two pieces. One piece that is that, one piece that is like that, with a plus and minus, depending if delta is 1 or 2. Sigma is the antipodal map that maps actually z to minus z. So I want you to recall that I have mapped my computation to Euclidean de Sitter. Normally, I am defining my grain function and my computation on this sheet, which is this one. But in a sense, I mean, immediately, my grain function know about the image one. So there is the sigma. Yeah, z is positive, and this one, because of the sigma, z is getting negative, and there's a plus sign. And the other thing is that this factor here, you just use some algebra, you sum and add, and then you can rewrite it as combine everything as an Euclidean distance. So it's really like what you would call an Euclidean distance, although it's curved space, it's not flat space. So it's massless Euclidean distance between the 2 points, and the bulk coordinate that is z for x and w for y. I decide to use a notation from quantum field theory to have a linear propagator, inverse linear propagator, that is introduce a vector that is pointing inside the bulk, so that u dot x is z, is the bulk coordinate, and u dot y is w, the bulk coordinate. And the thing that is amazing is that this epsilon here, which actually the presence of the epsilon here in this grain function and the hypergeometric was already discussed, I mean, some time ago in 78 by Alvis and company, when they look at the way to define actually properly the grain function in anti-de Sitter spacetime. So they look at anti-de Sitter, but for the case of that I'm looking at, you can just adapt what they did, turns to give you the high epsilon prescription, the natural high epsilon prescription you want for a Feynman propagator. So essentially, this is the thing that is very amazing, is that first, for the case of conformally coupled scalar in d dimension, so if d is not free, I mean, the formula changed a little bit, but it's the same because of the property of this hypergeometric function. So you have, without any effort, a computation that looks like curved space propagator complicated to something that is just quadratic propagators. I mean, and you have these linear terms because of the conformal invariance of the computation.
What is that the surprise? It's analytic space is conformally
I don't know. Nobody noticed that before. Yes. It's why is this hypergeometric collapsing to this thing? Yes, I mean it's a no, I don't know. I mean it's a the thing is that because the Laplacian here is complicated. So in a sense, I mean, and this is position space. It's not momentum space. So if you look at the differential operator here and you write it in your coordinate, of course, I mean maybe if you plug in delta, the values of delta, you will immediately get a form that is like that if you try to solve the differential equation, but that's not the natural way to do it. Okay. So now, equipped with that, then I can compute this correlator. So now I want to compute this 4-point correlator, phi 0, and I recall that actually the phi 0, your field after the Wick rotation has 2 components. A component that will have, in the case of the Sitter, I mean the Sitter space DS4, will have a component of conformal dimension 2 and a component of conformal dimension 1. Okay. So what's happening now is that your cosmological correlator in formalism is expanding on a component that is the phi minus, the phi plus, phi minus, because they are all these mixed terms, the phi plus, phi minus, etc., all the permutations, and all the phi plus. And this one are the field of dimension 1. This is 2 dimension 2, 2 dimension 1, and 4 dimension 2. And these correlator are multiplied by a power of the conformal term eta 0. So that means that when you do the late time expansion, actually this normally you would like to focus on that one because this is the piece that dominates the computation when you do the late time cosmological correlator. But in fact, if you do that, then you will lose the structure of the full correlator. So what we are going to do is that we are not just going to focus on the leading term, but we will evaluate all of them. So because this propagator looks like is the form of Euclidean position space propagator. You can draw actually your 4-point correlator where x1, x2, x3, x4 on the boundary. So then you can either connect this one with this one, this one with this one, and then there are all the possible permutations. Or you can have a bulk interaction, which is the cross diagram, or you can have a one loop, which is given by this, where this is the same field phi plus that propagates in the bulk and then run in the loop. But because your action here has this mixing term as well, you can, and this is the difference between this de Sitter computation compared to anti-de Sitter computation, that if you were just doing anti-de Sitter, you would just have one type of line each type, but here you have this mixing term where you have the delta equal 2 field that can run in the correlator for the delta equal 1 field. So for all delta equal 2 is the double line, so delta equal 2, but then here you have the delta equal 1 that can run, etc. And it's phi to the 4th, okay? And for the mixed one, this is what you get, okay? You get all this mixed one. Of course, what you have is that this is phi to the 4th, so you see I've never drawn anything like tadpoles. And of course, it's quantum field theory, so you have to do renormalization. So in fact, what I use as a notation here for my propagator are the renormalized dress propagator, where I have actually set the mass. So what we do is that we define the mass of my the mass m from this 2-point function by having absorbed, all the effect of the tadpole, as you would do, in flat space, phi to the 4th. And the effect of that is that all the divergent nature of the graph that are like infrared and UV divergences, there are divergences from when the bulk points collide together, will be transferred to corrections to the anomalous dimension. So the field initially they have dimension 1 or dimension 2, but due to the renormalization that you have to do for your quantum field theory in curve space, then you will have a correction to this dimension that will depend on the loop order. Okay. So it's trivial to compute the disconnected part. Okay, so the disconnected part is just given by the usual conformal ratio that we call V and Y, or zeta bar and 1 minus zeta bar, and they depend on the dimension of the field in a trivial way. Okay. And now you come to the first non-trivial graph, which is this cross. So the cross has this boundary to bulk propagator, and after conformal remapping, it takes a form that is like that. Okay. So this integral has been computing many times. There is no pretense of any originality in having evaluated that, and actually you as well has computed that. But I just want to show you to tell you how we do that. So the way we do that, well, is that I have used this notation from quantum field theory, where all the bulk propagators are linear propagators. And I want to compute that as if this is a dim reg, so as a quantum field theory amplitude. Quantum field theory flat space Feynman integral. So I didn't write the I epsilon prescription for short, but here this is a standard integral that you, when delta is an integer, that you can crack using the usual method. Okay. So the result for this graph is that there is some factor that depends on the dimension d. Okay. times something that only depends on the on delta. So as I said, I mean, actually, this object is what is called D in these papers, but we use a different notation. So if you use a parametric representation for that integral, after having stripped off this gamma function, gamma factor, you get something that depends on delta this way. And then you want to evaluate that. Okay. So it's totally it's a two-line computation using creative telescoping to show that actually this integral satisfies this recursion relation, so that I of delta plus n 0 to m times some coefficient that is a well, a polynomial in delta and n equals 0. So it's just some game about like the way you do partial integration and the action of the annihilator of the integrand, and so in a sense, I mean, it's a easy exercise. And what you do is that then you just need to for any n, you just need to compute the initial conditions. I mean, the delta for delta equal for delta equal 1 and delta and delta equal 4, to delta equal 4 for delta equal yes. So solving that relation when delta is an integer immediately tells you. If you solve, okay, so if you compute the value for delta equal 1, you plug delta equal 1 in there. Either you immediately recognize that it's going to give you the Bloch-Wigner D logarithm, or you use the program by Eric Panzer to get it. And so this function is a function of zeta and zeta bar, and it's a single valued D logarithm. There is no singularity on the real line because this one has a 0. And actually, if you compute all the values for delta equal 1, delta equal 2, etc., up to delta equal 4, then you can solve the recursion relation and obtain that actually for any integer delta, you have an expansion where the coefficients are well known and are rational functions of polynomials in zeta and zeta bar. And this is a single valued expression. So for delta equal 1, you get this. For delta equal 2, you get weight 2 single valued polylog. This is D logarithm. This is log of zeta zeta bar. So this is the log of the first cross ratio, and this is the second cross ratio, and you see the coefficients are there. And it seems that you could have poles, but actually there are zeros. So actually this thing always vanishes, I mean, to the right order, so that this function is regular on the real slice. So now we go to one loop. Okay, to one loop, then we have all this graph. So it looks like one loop Witten diagram, but because you're integrating over the bulk point, it's in this language of having map, I mean, treating these integrals at flat space, position space integrals, I mean, it's like two loop. So what you do get is that because here you have the sum of the field delta equal 1 and delta equal 2 running in the loop, it turns out the sum just takes a form that is very nice, that is very compact, where you have here the thing that comes from the measure because it's a curved ADS. You have the linear the linear propagator from the, so this is the boundary to bulk propagators that you have here. X and Y are the point here, and then here you have the contribution from the internal part. Okay, so the bulk to bulk propagator from X to Y, and as it is important, then there is the antipodal map that comes in, that allows you to rewrite actually the integral that was supposed to be just restricted to the upper Poincaré patch to the full space. So at the end of the day, you just have to evaluate that integral, which now has issues because it is divergent. Okay, when X goes to Y, there are divergences. So what we do is that we do regulate the integral by doing, oh, the xi should be downstairs, by doing some dim reg. So in a sense, I mean, there are many ways you try to regulate that integral, but one way that is natural when you see that expression is to use dimensional regularization. So the dimensional regularization, that means you compute them in 4 minus 2 epsilon. Without changing actually but you don't have to change the measure factor from the curvature, because if you do put an epsilon here and an epsilon here, the measure is still conformally invariant and it does not regulate the integral. So what you do is that then you do that, but de facto you break the conformal symmetry. Okay, fine, but still we will have to do renormalization at the end anyway. So then we do that. We have these the 4 minus 2 epsilon integrals. Delta is an integer that is 1, 2, 3, 4, whatever you want. But because we have broken the conformal invariance, there is one propagator that has the epsilon. Okay. And what you do is that you can just compute it. Yeah. This is and what you find is that there is indeed a divergence when the 2 points are coincident, and when the 2 points are coincident, as you can see, okay, that gives back this graph. Okay, so when the 2 points collide here, this is as if I had the cross. Here I had the cross, and you have no knowledge about the field that has been running in the loop. Okay, so yes, the same when the 2 points coincide, you have the cross with delta equal 2, etc. So you know that actually so it's expected that the 1 over epsilon pole is going to be the cross that I've computed before. No, and there's a finite part, which is given by this. Here, this mixed propagator is treated in a similar way. So you have as well a flat space type of graph. You can unfold, and then you get integrals like that with linear propagators everywhere. And then you can again evaluate them analytically using, for example, the program by Eric. And what you find that the cross that I presented to you before was a combination of, there is this Bloch-Wigner that is weight 2 single-valued polylog, then logs and rational piece. So this one was weight 2 and lower weight and single-valued quantities. So you won't be surprised that if I tell you that the finite piece actually is a weight-free single-valued combination. It's a single-valued combination of multiple polylog of weight 3 and lower. I cannot display the expression because they are pretty huge. So now,
Sorry, I did not get the one loop divergence is really proportional to the tree level or not?
Yes, it is proportional to the tree.
It's exactly the same combination of.
It is exactly it is proportional to that, and the coefficient is exactly this. And in fact, I will renormalize. I mean, I will compute the beta function. So the thing is that what you see, what is interesting is that if you try to disentangle the computation, and suppose you just want to compute the graph where you just propagate the delta 1 field, not do the sum that I did before. So you will have an integral that is of that form typically. So that integral looks very similar to the one I had before, except that you see you have here powers of the linear propagators. And locally, the divergence is the same. I mean, up to a factor of 2. So you get 1 over epsilon, then you get the cross, then you get a finite piece, which is the same as this finite piece that I got here, which is this weight-free single-valued multiple polylog. And here, there's an extra piece that turns to be given in a parametric representation by this expression. And this expression has a square root. And if you actually look at it, then you realize that actually this is an elliptic polylog. So the thing that is, I mean, we have discussed that in the De Sitter paper. So the thing that is pretty surprising, and that was not expected, I mean, before we did the computation, is that when you map the de Sitter computation to this Euclidean, because of the fact that you have to include the coupling between the field and this shadow, there are cancellations between the various contributions. So in a sense, the de Sitter computation of this correlator will not have this part that comes in because it doesn't have the coupling. It will already at one loop contains elliptic polylogs. And for delta equal 2, you will not get the elliptic polylog at one loop, but you will get them at two loops. Okay, and then in delta equal 1, you get K3. So, but curiously, in a de Sitter spacetime, because you have this combination of field that makes a sum of the diagram with the proper weight, I mean proper relative factor, then you get this cancellation, and actually the analytic structure of this graph is much simpler, and that is something that is kind of a surprise. Without having this variational principle from this action that was proposed by Di Pietro, Gorbenko, and Komatsu, discovering this cancellation would have required very, very careful analysis of tracking down factors of 2 and signs. So I imagine this is why people didn't notice it before. So now, as we said, well, the same typo, that we used DIMREG, a dimensional regularization of the integral. But DIMREG has broken the conformal symmetry. So the thing is that now what's happening is that we will then add the counter term, and the counter term will restore the conformal symmetry. So you have a phi to the fourth theory. Okay, so this is the phi to the fourth. And what we did is that, okay, then you renormalize your coupling, renormalize coupling. So this is mu, this is the dimensional parameter, so that you keep the dimension of, you don't change the dimension of the integral. And then there is the counter term here. And what you do is that then you fix the counter term so that you have your renormalized expression. Okay, so this is the renormalized coupling, this is the divergent expression, and then you sum the thing. Okay, so this is standard renormalization as you do it in phi to the fourth in flat space. You open a quantum field theory book. So that means when you have determined what is your renormalized coupling, lambda, you get an expression that is given by this. You can compute, as usual, the beta function associated to that, and you discover that if that this is exactly the expression that you have for the beta function for phi to the fourth in flat space, right? Because the divergence is a purely local divergence and doesn't know about the curvature of space. So now, once you have done that, the expression that actually broke, I mean, all this intermediate expression had totally broken conformal symmetry. If I try to do a transformation on my conformal ratio, I will never get the proper transformation. And another way to say that is that if I looked at the mixed propagator, the mixed correlator, where are they? Yes. Yes. So this one is a mixed correlator that is plus, plus, minus, minus, but I have as well the correlator that will have plus, minus, and minus, minus, plus, plus. And normally they should be related by conformal transformation, right? Because they are a function of the cross ratio, and if I do cross ratio, I can map one to the other. When I do the epsilon regularization, the expression that I get before renormalization doesn't satisfy that. I mean, it's broken. But once I have renormalized, yes, then the expression in terms of the renormalized coupling, when I sum everything like this, and in particular this mixed correlator, then you check it has the correct conformal invariance. So everything is totally fine. And we have a consistent scheme that, okay, so I've explained to you how it works at one loop Witten diagram, which means computing this two loop flat space like diagram, but it works as well at the next order, the two loop Witten we looked at, but the integral are much more complicated to evaluate. But for the renormalization, you don't need to have the full evaluation of the integral. So one of the things still that we have checked is that it's possible to use a different regularization scheme. So Ivo and Igor Bertrand proposed a few years back a regularization that preserves actually the ADS symmetry. So essentially, you try to put a little ball to excise the region when the two bulk terms they go together, but you can do that in a way that preserves actually the conformal invariance. So that makes the form of the propagator much more complicated, but to the one loop order, we have related the two schemes. So of course, there are two renormalization schemes. So that means, of course, the divergent part. So if you call delta the size of the little ball that they used, the coefficient of the log delta and the coefficient of the epsilon pole is scheme independent. So they have to match. But the finite piece is not. But once you have done the renormalization and you extract the physical observable, like the correction to the anomalous dimension, then they have to match. And so we have complete control of the two schemes, actually to one loop order, because in that scheme, it's very difficult to go beyond one loop. Okay. So now, what do I want to do with that? So as I said, the motivation for this is to try to understand quantum field theory in the zeta space. And the thing is that we wanted to understand if we have a setup that so here I have focused on the evaluation of these integrals and the explicit expression in terms of single-valued polylog or elliptic sector. But if I look at them from, this is an identity. If I write the I epsilon prescription, I can then try to understand what is unitarity. Okay, so I know when I look at this integral, what would be unitarity cut, right? In a sense, the way you define unitarity cut in quantum field theory, then you want to cut lines here or lines there, and then you know what you do because you have an expression here that is prescription for the multivalueness, and then you can identify the singularity. Another way to say that is that okay, so if you use the parametric representation with the I epsilon, so the I epsilon actually would go into that factor here. So there's a term that will be plus I epsilon somewhere here, and there is some. You can look at the positivity constraints on this polynomial and solve the Landau equation. So essentially you can rerun what you have learned from the book by, for example, Dixon and Zuber, how to relate the analytic properties of this function in the complex zeta plane, and see how it matches with your intuition about what you call causality and in quantum field theory. So that is essentially the physics output that we want. So we want to make sure that we have a formalism that allows us to analyze this question in a precise way and try to understand what is quantum field theory in the zeta space. Now, in a sense, this computation that I've presented to you, we need to check whether or not that makes sense really. Because there is, at the beginning, I told you there is a way that we treated this correlator by doing this analytic continuation and using this effective action to compute, to organize the computation. So one way to do that is to relate, to extract from the computation we did, physical quantities. And one of the physical quantity is to precisely look at what are the, after renormalization, what are the correction to the anomalous dimension of the field. So the field, my field that are the external field that have classical dimension 2 and 1, they will get correction after I have removed the divergences, and the correction will depend on the loop order. On lambda is my complete constant. Okay. So this you can do. Well, then what you do is that you have to use the conformal block expansion, and well, in a sense, the standard reference for that is this. No, the problem is that because we have delta equal 1, delta plus and delta 2 is delta minus is 1 and delta plus is 2, we have a degeneracy in the dimension of the field. So this is the expansion in terms of this is the derivative of the field. And so this is the spin, and this is the dimension. So it counts the number of operator I have here. But you see that all these guys are integer, and because delta 1 is 1 and delta 2 is 2. So the case when you have 1 plus 1 plus 2n plus L, 2 plus 2 plus 2n plus L, or 1 plus 2 plus 2n plus L, there are clearly cases where you can find n and L where different values of delta 1 and delta 2, give you the same dimension. Because you have mixing, then it's complicated to try to extract the because we have to extract the correction to the anomalous dimension and the conformal block, as well. So you have to diagonalize them. So what we did is that we decided to change basis so that the 2-point function between a symmetric. So essentially, you define operator that is a symmetric sum of the delta 1 and delta 2 and the antisymmetric one, so that the 2-point function of this guy is 0, and this is normalized this way so that you can extract the information for your computation. So once you have done that, then you know what are the correction to the animal the correction to the dimension of this operator depending on n and L. Okay, and the box is for 2 derivatives here, and what you get is this. Okay, so you get that, for example, 2 plus 2nl plus this sum, infinite sum, that depends on lambda, and this guy of order, yes, at one loop it's lambda, then lambda square, etc. So gamma is the coupling constant divided by 6 pi square, and then you have this expression there. And in fact, what you find as a contradiction to, in difference to what you would do in the Sitter space, is that you see that there are degeneracies, which is very new. And I think it's a consequence of the fact that when you define this in informalism, you have to look at this closed time curve, and that forces you to consider this correlator defined from this, that mixes actually the field and its shadow. And that couples the two CFT associated with this generalized field on the boundary. So as a conclusion, so what I'm saying is that actually we can actually explicitly evaluate the cosmological correlator in this way. I've described the case of the conformally coupled scalar field, but because it's where the expression are the simplest, we can do that as well for any delta. Any integer delta. If delta is not integer, this is different because the bulk-to-bulk propagator needs to be treated in a different way. And what we find is that we do find that actually if you start with 2 generalized free field of dimension 1 and dimension 2, then from the cosmological correlator, you find that the dual CFT, exhibits some coupling, and the coupling between these two guys is actually responsible due to this mixing between the field and its shadow through this effective action that we introduced at the beginning. So if you were looking at not the Sitter 4, but for example the Sitter 5, so that means the boundary component would be even, not odd, then in the 5 to the 4th expansion, you will have a different type of coupling, which is, again, a different structure, and there will be, but the analytic structure is very similar, but the mixing would be totally different. So, so in a sense, we know, I think it's going back to the motivation at the beginning, which is to understand what is quantum field theory in the Sitter spacetime. Well, I think this analytic evaluation of this correlator, the fact that we can evaluate them, and thanks as well to the program by Eric that allows us to crank this the expression in terms of multiple polylog, then we are getting a more deeper insight into what exactly is the quantum field theory there, and in particular we have a tool now to address the question of unitarity and analyticity in the Sitter space-time. Okay, so this is where I stop. Thank you.
Thank you, Pierre. I see already the first question. I walk around with this, except that it doesn't work.
Well, maybe normally, if you've got a 5-4 theory and
Yes.
you want to get a conformal field theory, you have to go to the Wilson-Fisher fixed point.
Yes.
But are you claiming the exists form of conformal field theory in strictly 4 dimensions in the context that you're discussing?
Yes, I think yes, and I think I don't have to go to the fixed point. Yes, this theory exists. Yeah,
I mean,
so the renormalization scheme we are introduced is mimicked really on what you do in flat space, right? So from the 5 to the 4.
Yeah, but does your renormalization scheme involve introducing some arbitrary mass like you would normally in dimensional regularization? Because in standard dimensional regularization, there's a mu.
There's a mu, yes.
And
so
you know,
indeed, okay. So that's the mu that I introduced here, right? Okay. So that's my mu. Mu is there for keeping the dimension fixed.
Yeah, but does that not appear in some of your finite functions as scales of logarithm? I mean, normally, when you compute a 4-point function, you'd have something like log s, where s is a Manstein variable over mu squared, I guess.
Okay.
It's your theory of conformal, Pierre, right? It's the conformal symmetry of the boundary that you get.
Yes. So the thing is that, of course, okay. So here I have a mu square, right? Mm-hmm. Here I have an epsilon pole. So indeed, there is something normally that the mu would be there. Okay, but there is a sum over the 3 sectors. And there's no mu. So mu cancels at the end in the finite
that
piece.
Particular quantity there is not conformal, is that right?
So that particular quantity, once I have dim-regged, is not. Mm-hmm. But if you do indeed the expansion, so normally you would say that indeed there should be a log mu square somewhere. Mm-hmm. So in my log, I have log of the cross ratio. You would say, okay, then I have a log of mu square. My cross ratio is dimensionless, mu is dimension full, so it's not clear normally would it would fit. But in fact, I mean they cancel. I mean it's in that sum. So, but what's happening is that when you compute the when you so here the beta function is defined as the logarithmic derivative with respect to mu, of course, as usual. If I don't have a mu, I cannot get what is beta.
Yeah, but normally to get a conformal theory, you want beta to be 0.
I want beta to be 0, indeed, but it's conformal on the boundary, right? So
it's not a conformal.
Yeah, right.
It's not a conformal theory.
Maybe I've missed it somehow.
So the thing that we are the thing that we are that we restore after renormalization is the for example, the symmetry between all this mixed correlator, right? So you can act. It's a function of the cross ratio, right? This is everywhere a function of the cross ratio. So, for example, you can look at the way this thing behaves when you act with the various cross ratio, right? And then you have the dual theory on the boundary, which is precisely the CFT that is conformal itself. So the regularization assures that the boundary theory is conformally invariant, which you could question that because it's de Sitter, okay? But we have done the same computation before in anti-de Sitter. Anti-de Sitter tends to have this elliptic sector. It's a little more complicated, but the same scheme applies.
Your theory on boundary is conformal for arbitrary elements.
On the boundary, yes.
Any other questions? Yep, Herbert, I'm coming.
I may have misunderstood. But do you get an expression of this correlator or this 4-point function both in classical multiple polylogs and in elliptic
yes.
polylogs?
So
you get a function equation of those two.
So that is the okay. So the thing is that this integral here as a piece that yes, this guy mixes to elliptic and non-elliptic. And if you go to higher loop, then you are going to get more and more. Okay, so the dimension. So then you get K3 and etc. etc. So in a sense, there's a mixture of terms. Yes. So it may be bizarre because it doesn't seem to be keeping the type of transcendentity of function, but that is just yeah. I mean, there is.
But they don't describe the same object. They describe different parts of your integral.
So what you do is that here you just use tensor reduction, and then you split off the effect of this numerator, and then there is a pieces that is not elliptic, and there's a piece that is elliptic in that one loop. So.
Any other questions?
Thank you. I did not get what were your anomalous dimensions. The wave functional normalization is only at 2 loops, right? So what you do is our composite operator. What are the composite operator you consider?
Oh, my composite operator are.
Yeah, I don't know what O is. Sorry.
Well, it's either phi plus or phi minus. So I have this. So this is the OP.
So they are bilinear with arbitrary number of derivative of phi.
Yes. It's a double trace. It's the double trace sector, and there's no gravity. It's totally rigid. So, right. Okay. So that is the way we do extract this. So that's the number we extract.
So those dimensions are the same as those computed by Wilson.
Excuse me?
Those dimensions are the same as those computed by Wilson.
Yes. Yeah, I think so, because locally, I mean, it's like as if this is flat space. And so we have here expression for any finite value of n, but when you take the large n or large L, we could compare to some numerical work by people doing bootstrap or something that done by Gibredov, and this matches. But we have the expression for all n and L. So, and the bootstrap people can only get the asymptotic expansion. So
one look at the bootstrap, they do
yes.
perturbative.
Well, I mean, when you look at the perturbative contribution, they can compare to the one loop and 2 loops, but they don't get the finite value of they don't get all the finite n and L values. They get the asymptotic one, and this matches perfectly well. So in a sense, I mean, I would say that this validates the procedure that we used, which is this way of renormalizing is maybe not a standard way to treat the renormalization of the Witten diagram, but it seemed to be actually working and giving the right data. So.
Right. If there are no questions on the Zoom call and in the room, let's thank Pierre again. And this concludes the morning session, and we will reconvene at 1:30 after lunch.